Hey there, Eric from TI here, and today we're going to explore the mysteries of electricity. Have you ever thought about how the lights in your home work? You go over to the wall, you flip a switch, and voila, you have light. Well, how did that happen? How does that whole process work? Why is it that I can go over to the wall, I flip this switch, and then all of a sudden I get light turning on that's in a different location from the original switch? Well, today we're going to use a simulation that will allow us to make some virtual circuits so we can better understand the relationships between current, voltage, and resistance. And hopefully by the end of this lesson, you'll have a better understanding of how the lights in your home actually work. You're welcome to follow along this video. You can pause it at any time to take notes. If you'd prefer to interact with the simulation yourself, you can visit our website at www.education.ti.com and download the TI-Nspire CX Premium software. To use this lesson, you're going to want to go to www.scienceinspire.com, and then you can find the lesson titled Circuit Construction Kit within the category Physical Science. Okay, with that, let's get started. Okay, so now I have the lesson titled Circuit Construction Kit opened up in the TI-Nspire CX Premium software. Unlike other Science-inspired lessons, this one only has a couple of pages. I'm going to ask questions throughout the presentation, the video here, and then talk through what the answers might be. So we're going to run through some different scenarios on the sort of simulation play space here. We're going to build some different circuits and find out how the relationship between current, voltage, and resistance might change when we add some of these different components over here. All right. So the first page talks about building circuits with resistors, light bulbs, batteries, and switches. And then we're going to take measurements using a ammeter and a voltmeter. So an ammeter measures amps or current, and a voltmeter measures voltage. So we're going to look at the circuit as a schematic diagram throughout this video as well. And then we'll take a look at the actual simulation to kind of map those things together. All right, so in the sim, we're going to take components from our toolbox, which I think I showed you. On the right side of the page to build a circuit, we're going to select a component from the toolbox and add that component to the virtual circuit area. And then we're going to click and drag some things to connect it all together and test things like light bulbs, making sure that those work the way we expect them to. If toward the end of the video, we're going to probably try a couple of the light bulbs and see how that works compared to just a single light bulb. We're also going to look at the voltage and the current while these things are turned on and off, just to show that when the switch is open, there's no electricity flowing. When the switch is closed, there is electricity flowing. All right, so let's go ahead and go over here and take a look. In any circuit, you have to have some wire. Okay, so we're going to click and drag some of the wire over here, and then I can make the wire longer or shorter. I can also rotate it. And for this simple circuit, we're just going to grab, I think, about 6 pieces of wire, and then I'll start building the circuit. So in your home, behind the walls, there's copper wire running up and down the walls into the ceiling that helps control the lighting that's in your house. And so this is sort of maybe a virtual example, if you will, of what's going on when you turn on the light switch. Okay, so this will help hopefully clear up some of the sort of the mysterious aspect of, hey, when I click that switch, the lights come on. Why does that happen? Well, like I said, hopefully this will help us evaluate that. All right, I think I'm going to make this one a little bit bigger here. Just leave myself some space. And by the way, you can do this on the software like I'm doing, or if you have a TI-Nspire CX or CX2 graphing calculator, you can also do it there. Do it right on the calculator. So it's whatever you have access to. You can participate in manipulating these kinds of things on your own. All right, whoops, almost messed that one up. There we go. And I'm selecting and clicking. All right, so I've got 2 sides of my circuit built. And I think what I want to do now is I'm going to add a resistor on one side. So we'll connect that resistor here. Oops, I gotta take the wire, move that over there. Boom. Alright, so now they're all connected. The little green circles tell me that I'm good to go. And in any circuit, you have to have power. Now the difference here, we're using a battery for our power, which is direct currents, DC, direct current. In your house, you're using AC, which is alternating current. But the thing that's the same between those two is that the battery provides power, and your house, the electric company, provides power to your lines, to your lights. So that's all coming from whatever city you live in or municipality. They usually use fuel or they burn coal. In some rare instances, they might use nuclear or hydroelectric power, and then when they generate electricity, they send it out over the wires and it goes into everybody's homes. Kind of neat. But for this simulation, like I said, we're just going to use a battery. So we have our circuit built, our first circuit, and we're going to turn that on in a second. But before we do, I want to show you this diagram. So this is a sort of another way to look at how circuits work. And some of the symbols that are used, you'll notice in the image there's a R for a resistor, and you'll see a little picture of a light bulb, because a light bulb effectively is a resistor. And so we'll talk more about resistors in a bit. The V represents voltage, and that's basically your power source. So that's the battery, and that's the symbol we use. You'll notice on the left side it's plus, on the right side it's minus. And then those little arrows in the corners represent the flow of current. They represent the flow of electricity, the direction of electricity, and they're denoted by the letter I. But you'll notice that the current flows from the negative side of the battery. Okay, it leaves the negative side of the battery, goes all the way around, and then returns back to the positive side. All right, so that's something that you want to pay attention to. We're going to run our simulation in a second just to verify that. All right, back on the simulation page, and so we have our wire. These little blue dots represent the flow of electrons, the flow of electricity. So basically the electrons should leave the battery and then flow through this copper wire into the resistor, and then back out, and then back into the positive side of the battery. So when we turn it on, I should say when we press play, it's not quite right to say turn it on. It's a closed circuit. There are no breaks. So once that power supply is there and you complete the circuit, electricity is flowing. There's no turning it on or turning it off. It's just always on, because I don't have a switch in here. Okay, but you can see the flow, the little blue dots kind of flowing through, gives you the direction. That's exactly what we showed on the on that diagram. So I'm going to pause this for a second, and I want to take a look at another diagram, just to kind of show you what the symbolism is for resistors. Here's that diagram, and what we see is it's the same direction. Everything's the same as the previous diagram I showed you, except for this part. So instead of the light bulb serving as the resistor, we have this sort of generic zigzag line. And in general, this can represent resistors in a circuit diagram. So here's the battery. We got the plus side and the minus side. You'll notice that the lines decrease in size. The direction of the arrows kind of tells us that that's the negative side, so the direction of current is going this way. So these diagrams are important because you can kind of draw out your circuit before you actually try to build one. And chances are, if you're taking, if you're doing this in a lab with real wire and light bulbs and batteries and that kind of thing, drawing out your plan before you try to actually build the circuits probably it makes things a little more efficient and probably a little safer. So just keep that in mind. But that's what these symbols look like. If you go to a hardware store, you'll see things like this in the electrical department. If you're picking up some kind of test kit of some to test electricity. So these symbols are fairly universal. All right, let's get back to the activity right here. And so we saw that that the flow of electricity is moving from negative to positive. So from negative to positive, that's the flow of electricity. And then I want to jump back over real quick to another diagram. All right, so this one, same exact thing we saw before, but you'll notice that now we're separating words with letters, essentially. So basically what we're doing is we're saying, okay, we had a bulb here, we described resistor, now we just have the symbol, the letter R, so we can use that in an equation in a little bit. And then instead of saying battery here or voltage, we just have the V, and we have the I. So these letters are just variables that we use in an equation to try to figure out, okay, if I know voltage and I know current, then I should be able to figure out resistance. Or if I know resistance and I know current, then I should be able to figure out voltage. So there's a relationship that that these things have. And so let's see, what else can I show you here? Let's go over to the next one. All right, so now we're going to introduce this idea of a switch. And basically a switch is like the light switch in your home that I mentioned earlier. When it's off, it opens the circuit. It means that there's a break in the circuit, which also means there's no current running through your circuit. We say that's open. Okay, now a closed circuit means that this little switch is closed, which means your lights are on because it's a continuous circuit. The wires are touching one another, therefore there's a flow of electricity. So sometimes people get confused between the term open and closed. Sometimes people think closed means that the light is off. I've even heard students talk about closing the light instead of turning it off. And so just be careful with that terminology. An open circuit is off. There's no current flowing. See, current stops flowing. A closed circuit is on. There is electricity flowing. So just so just be aware of that. All right, so now what we're going to do is I'm going to add the switch. I want to see what happens when we add this switch into this circuit. So what I need to do is, I need to take this piece of wire off of here. I need to break that. Let's see. I'm just going to take it out altogether. And I'm going to take another piece of wire. Oops. Connect it there. My switch. I think I can turn it. Yep. And we're just going to take the wire from here, connect it there, and I need another piece of wire. I'm going to connect there and then pull it down to here. And right now, when I click on the switch, it says it's open. And we said that when the switch is open, that means that it's off. But if I close it here, okay, switch is closed, I run the simulation, all is well. If I open it, no current's flowing. Closed, current's flowing. Okay? Open, nothing. Closed, flow. All right. So going back to our image here, so the simulation we just did is this. It's this diagram right here. Okay? All right, back in our simulation. And here what I want to do is I want to do some measurements now. So we have our resistor, we have our battery, which is our voltage source. We have a switch to open and close the circuit to turn it off or on. So open circuit is off, closed circuit is on. Okay, so what I'm going to do now is I'm going to use a voltmeter, and we're going to put the different leads across the resistor. And what we see is we're very close to 9 volts. So we have about 9 volts. And then on this one, this is our ammeter, and we can use this to measure anywhere on the circuit. Really, you can measure how many amps, what the current is, and it says that we have 0.9 amps. Okay, and so whether the circuit's running you have to have the circuit running in order to get those measurements. And so we've switch is closed. I've got the simulation running, and you can see those electrons flowing through the circuit. And we have some values for our voltage and a value for our current. So what we don't know is the resistance, and so we've got to figure out what the resistance is here. All right, so this image, you've seen this several times already. Resistor, battery, current represented by the direction of currents represented by the arrows. I got a closed circuit, but we saw a value for voltage. It was about 9 volts. A value for current, it was 0.9 amps. We didn't see any values for resistance, and that's kind of our unknown at this point. And so in order to figure out the value for resistance, we need to understand this equation. V equals I times R. In other words, voltage is equal to current multiplied by resistance. Now the thing is we can manipulate this equation to get R by itself. And the way you do that is we have to get I from over here to over there. And so we can divide both sides by I, by current, and that'll cancel current over here on this side and put it over on here as V over I. So in other words, we'll have an equation that looks like R equals V divided by I. Resistance is equal to voltage divided by current. And so that's what we're going to take a look at here on the calculator. So if I'm going to pull up my little calculator screen right here, and we said that we can manipulate the equation so that it looks something like this, V divided by the letter I, and that's exactly what we're going to do. So we know the value for V, we know the value for I, so then we're going to go ahead and plug those in. So 9 volts divided by 0.9 amps gives me 10 ohms is the unit for resistance. So it's spelled like this, ohms. Okay. And so so now I know what my resistance is. That was what's called a 10 ohm resistor. Whoops. So let me get back to the simulation. Whoops. There we go. All right. And so so now I know that this resistor is a 10 ohm resistor, and when I click on it, we can see that right here. Okay, 10 ohms. The little symbol here is the omega. Omega is just it's a Greek letter, and we use it to represent the unit for resistance as ohms. All right, now I want to see what happens when we substitute our resistor for an actual light bulb. So this is the diagram that we're going to try to model with the simulation. And just a real quick description here. So one of the most common uses for a circuit is to power an electrical device, and one of the most common electrical devices tends to be a light bulb. So like I said, think about your home and all the lights you have in your home. And so we have a light bulb that's connected in this diagram, has its own resistance, its own voltage, and has current flowing through it. So we're going to jump back over to our simulation, and I'm going to take these off of here, and then instead of this, I've got my resistor selected. I'm going to throw a light bulb in here. It may take me a second to get the everything hooked up. Looks like that one hooked up the wrong place. All right. Yeah, substituted my switch. Look at that. All right, here we go. Okay, so I'm going to put that there, and boom, got it. All right, now we're connected, and I got my switch. I have the battery. I'm going to go ahead and pull that voltmeter up one more time, and we're going to check it across voltage, or check it across the resistor. Oh, there we go. Get on there. All right. Nope, not quite. All right. All right. No voltage is happening, obviously, because we don't have the circuit closed. And my amps, my current, I can put that over here. I'll just put that there. Oops. There we go. All right. So I'm going to close the switch. Look at that. We have light. Fantastic. All right, but for some reason I don't have any readings on my amps. Let's see. Oh, there we go. Okay, just had to reset it. Looks like, and I must not have gotten these terminals on there quite right. Okay, there. Oh, there it is. Okay, so 9 volts again and 0.9 amps again. So you know, using that voltmeter and my ammeter, I can tell how much electricity is flowing through this circuit. And the same thing, I mean, if you were to calculate resistance here, it's going to be the same value as before. It's going to be up here. I mean, it's the same idea. But yeah, so we had 9 volts divided by, whoops, there we go, divided by 0.9 amps, and obviously I get 10 ohms of resistance. So that is the same. The only difference in this between this circuit and the last one is that my resistor is a light bulb instead of just being a straight up resistor. Okay, so that's about the only difference that, you know, should concern you. Everything else is the same. The values are all the same. Everything else is identical. All right, so let's go ahead and change pace here. Okay, so we saw a circuit with one light bulb, one resistor. Now we're going to try something a little different. We're going to do 2 resistors. And so let's see. So basically the equation doesn't really change much. The only difference is we add that other resistor to the total resistance. So in other words, voltage still equals current times resistance. But this time we're going to use 2 resistors, so we have to take the sum. We have to add all of the resistors in the circuit, so 2 of them. So this, you know, it's not really that complicated. And what we're going to do is we're going to solve for current this time. So we know what voltage is. It's still 9 volts. And resistance is 10 ohms plus 10 ohms. That's 20 ohms of resistance. And so theoretically we can figure out what the current is going to be. All right, so I, or current, equals voltage divided by the sum of the resistance. So I already have that set up for you in the simulation. So I have 2 light bulbs, each of which is still 10 ohms. Yep, both are 10 ohms. And my voltage is still 9 volts. So I have a 9-volt battery. And so, you know, let's do the theoretical part first. Let's see what the math looks like. And I'm going to clear this out a little bit. Let's see, clear A to Z, clear history. Let's do that. So let's take a look at, okay, so I said my voltage was equal to 9 volts. And we said our resistance was equal to 10 ohms. I have the symbol for ohms in front of me, plus 10 ohms, which is a total of 20 ohms. All right, so that'd be 20 ohms. And we're trying to solve for current, so we want to know what current is. So look, we've got 9 volts for voltage, and we've got 20 ohms for ohms. All right, so now let's do the math. So we know that, we saw the equation earlier that current, we could solve for current by saying, okay, if V equals I times R, and I want to get I by itself, I know I have to divide by R on both sides, which means that I is going to be equal to V divided by R. Okay, so we're going to divide voltage by resistance. And when we do that, we say 9 volts divided by 20 ohms, and that's going to give us, wait for it, all right, 0.45. Okay, so what happened? Earlier, when we did current, we saw our ammeter read out 0.9 ohms. Now we're saying we have 0.45 ohms. There seems to be some sort of relationship between current and resistance. So let's take a look at that. Okay, so current and resistance. When current is on one side and resistance is on the other side, resistance is in the denominator and current is in the numerator. So what that means is as you add more and more resistance to a circuit, that denominator becomes bigger and bigger. And as you know, when you divide a number by a number that's bigger, the result is going to equal a number that's a little bit smaller. So in other words, before we had our current was 0.9, our voltage was 9, and our resistance was 10. But now the resistance is 20, and the voltage hasn't changed, so 9 divided by 20 as opposed to 9 divided by 10, well, you can see why the number got cut in half, because the resistance doubled. So when I doubled the denominator, I cut the other side of the equation in half, is basically what's going on. Okay? And we can verify that with our simulation. Just pull up our ammeter here, and 0.45 amps is what we see. Okay? All right, so hopefully that one made sense. And while we're here and while we're looking at this one, I'm trying to get rid of that ammeter. There we go. Let's take a look at the voltage across one resistor versus both resistors. Voltage across one resistor is 4.5 volts. Okay. Now if I take this other lead and I put it over here, we're back to 9 volts. Because the entire circuit is still being powered by this battery, and this battery is 9 volts. But when you do it across each individual resistor, you would expect the voltage to be cut in half, and that's what we saw. So that's very interesting. Now let's try another scenario. Let's say, okay, well, if that's true, then if I add a third light bulb, what would I expect to see in terms of voltage and current? Well, we're going to test that out. I'm going to move this light bulb. I need to add a little bit of wire. So let's see, I'll put that piece there. This guy goes up there. And then one more piece of wire. Actually, I don't need that piece of wire. I'm just going to grab this end. Bam. All right. So now we have 3 resistors in the circuit. So, let's go back to the calculator. Voltage doesn't change in the overall circuit. We divide by resistance to find current. This time I'm dividing by 30 ohms because I have 3 10-ohm light bulbs. And what I should see is the current was cut again. This time it's a third of what it was before. So it was, when we had one light bulb that was 10 ohms, we had 0.9 amps of current. Now that we have 3 10-ohm light bulbs, now we have a third of that. We have 0.3 amps. Okay, and so current is what flows through the circuit. It's moving. Resistors resist the flow of electricity, and so this kind of makes sense that even from a conceptual point of view, that my current value is decreasing. Okay, and the same thing here. We could do it mathematically. We'd say, what happens if I had 4 light bulbs and I had 40 ohms? Well, 9 divided by 4 is 0.225. So you kind of get the idea here. The more current, the more resistance you have, the less current you'll have. So current and resistance, and this is a key point here, current and resistance are inversely proportional, meaning when one goes up, the other has to go down. Whereas voltage is directly proportional with those other values. Okay, so voltage goes up, either current or resistance or both will also go up because V equals I times R. Okay, but the key point here is that resistance is inversely proportional with current. All right, so let me jump back over here real quick. We did 4 light bulbs, so I'm going to do a little trick here. Instead of adding a 4th light bulb, I'm just going to double the resistance of one light bulb. So I still have a total of 40 ohms. So I've got 20 in this light bulb, 10 in that one, and 10 in that one. Okay. So now when I take my ammeter, we said that, well, with 40 ohms I should have 0.225 amps. And here, yes. So I don't have the third decimal place, but it's a good estimation. 0.22 amps is what I would expect. It's what I got. And then if we take a look at voltage, voltage across across both resistors shouldn't change much. It shouldn't change at all, actually. Yeah, 9 volts. But voltage across a 10 amp or a 10 ohm resistor is cut into a fourth. So it's 2.225, or sorry, 2.25. If I do it across two 10 ohm resistors, two 10 ohm light bulbs, a total of 20 ohms, the voltage is cut in half. And when I do it across one light bulb that's 20 ohms and the other two are 10 apiece, I'm back to 9 volts across the whole thing. So let's see, what would you expect to happen though if I left and moved this over here? What number would you expect to see if I'm looking at the voltage across one resistor, but it's a 20 ohm resistor? Would you expect to see 9 volts, 4.5 volts, or 2.25 volts? Well, let's see. Looks like half, okay, so 4.5 volts. Okay, so that does make sense. It's consistent with what we saw over here. We're looking at not really the number of light bulbs, we're really looking at the total resistance. Okay, so the sum of these two light bulbs is 20 ohms, which is equal to this one light bulb's resistance, which is also 20 ohms. Okay, with that concludes this lesson. If you'd like to try this on your own and play with the circuit construction kit, you are welcome to go to our website at www.education.ti.com, download the TI-Nspire CX Premium software, and then go to www.scienceinspired.com to download this activity under physical science. I hope this made a little more sense to you. I hope Ohm's law isn't as scary as maybe it was when we started this activity. It's really just kind of understanding the relationship between voltage, current, and resistance, and knowing how to solve for any one of those values. But now you probably have a better sense of how the lights in your home work. All right, that's it for this lesson. Hope you enjoyed it. Hope Ohm's law, it makes a little more sense to you. And please check out our YouTube channel for more student videos at all one word, TI Calculators. So TI Calculators, all one word, just search on YouTube and you'll find us. Thanks so much and have a good day.